Well, happy St. Patrick's Day. Let's get Notability out, get our notes up, and we're going to continue where we left off yesterday. At some point, you guys are going to need to go into eBackpack and grab the next set of notes and just add them on. I'll give you guys a second, and we'll begin. The hydrologic cycle, which we were talking about yesterday, the different phase changes, solid, liquid, liquid to gas, forming clouds, how evaporation is putting water into the atmosphere and moving from one reservoir to another, really is all going to be driven by the sun. Because we call it a cycle, it means that it has no beginning or no end. And if you look at the diagram that's up here, you can see that precipitation, transpiration, runoff, infiltration, which is not actually on here in yellow, but you can see the arrow on the right over here is indicating infiltration. You'll recall from yesterday that infiltration is going to supply the groundwater reservoir or aquifer with water that then we'll use later on for drinking water. We'll learn about irrigation, a lot of different ways that groundwater affects our lives. So you guys can all see in this diagram the hydrologic cycle and how the evaporation leads to condensation, which then makes clouds. So let's all remember that clouds are not actually gas, but rather a liquid or crystal solid. And then when the clouds reach their full capacity, you'll start to get precipitation. Please understand, when we use the word precipitation, we're not saying it's raining, because as we saw the other day, it could be snow, it could be sleet, hail. These are all different forms of precipitation. Now it's time to write. So we're going to do a lot of notes today. You guys are going to do a lot of fill-in, so try to keep pace and do your best. So let's talk a little bit more about the different phase changes and the processes that make up the hydrologic cycle. Now, yesterday we talked about evaporation. We went through some different examples of how liquid changes over to a gas, and we used examples in some classes about the way that your hair dries after you took a shower, or when you hang a towel up after a shower, the way that the towel dries. That's all evaporation. But evaporation is very simply just taking liquid and changing it into a gaseous state. Now that's going to require that we put energy into the molecule. So when you guys looked at the diagram at the end of class yesterday, it talked about energy being absorbed, and there's the latent heat of evaporation. You have to put a certain amount of energy in order for evaporation to take place. Condensation is just the opposite. So that's when energy is going to be released and you get the phase change from gas back down to liquid. So this is going to be crucial for cloud formation, and we'll do a whole section on clouds. You guys are going to be able to identify all kinds of different clouds up in the sky. However, in the meantime, let's keep moving. What happens when we get too much condensation? Well, the water droplets start to get so heavy that gravity can take over and actually pull it out of the clouds, coming down as either rain, sleet, snow, hail, all these different forms of precipitation. So let's remember that that's pretty important, that we not just go, oh, precipitation is rain, because it can be a lot more. And then my favorite word of the chapter, sublimation. And sublimation, of course, is when a solid goes directly into a gas. The best example most people would know would be dry ice. However, I talked about in your freezer where you could have some ice cubes. If those ice cubes haven't been used for months or maybe even years, if you like going to grandma's freezer, you might be pulling out an ice tray and it's like, why are these little chips of ice in your ice tray? Alright, but we'll stop picking on grandma's ice trays. I'm going to give you guys a minute to just finish up whatever notes you need to fill in. And if you still need this information, this video will be on my website all weekend. Feel free to go check it out. Alright, melting, freezing, and deposition. Melting, we all know, is what happens when you let your ice cream sit there too long, right? Or what all the sports kids are hoping happens out on the fields. But melting in general is just a solid changing over to a liquid. Energy must be absorbed, so there's going to be the latent heat of melting, just as you'll have the latent heat of freezing, and that's when energy is going to be released when you take water and you slow it down. It's a good point to mention that temperature, by definition, is the average kinetic energy. You might want to put a little note somewhere, right? Temperature is the average kinetic energy. So when we say that something has a low temperature, we're actually saying that it has a low amount of motion in its molecules. So freezing, think about it, when freezing happens, things start to slow down. When melting happens, we're starting to speed things up. Hopefully that helps some of y'all. Next we have deposition. And deposition is when a gas passes over a really cool surface and it goes straight into the solid form. So there's no time in the liquid state. You'll see that as frost on the lawn, usually in like November. We might still see it at the end of March into April. But you need enough moisture in the air that it comes across, and then those little blades of grass are just kind of sticking up there, and as the air passes through, it can just make that transition. So I want you to think to yourself, is deposition energy absorbed or energy released? I hope none of you are raising your hand because I can't actually call on you. However, the answer you should have would be energy released, because you're slowing gas molecules down into a solid. They're bouncing all over the place and then boom, they're stuck in place. By the way, a solid doesn't mean that they're not moving. Their just vibrations are so small that they're not moving about the room. Cool. Next slide. Transpiration. Now, transpiration is the release of water vapor into the atmosphere by plants or animals. And if you all take your hand right now, put it over your mouth by maybe 3-4 inches, and then just go. You'll feel that the moisture in your hand got a little wet. Sometimes you guys do that on the school bus window because you're bored. You put your nose real close and you go, right, and then you draw a little message. That's water vapor being released by an animal. Plants do the same thing. So either example you want to use, whether animals or plants, you're talking about transpiration. Evapotranspiration is the combined effect. So you think about that puddle outside because of the melting ice and snow. Well, once that starts to evaporate, plus the plants out there in the courtyard are also adding water vapor into the atmosphere. You put the two together, you got evapotranspiration. Can I get it too easy? Alright, I'm going to give you guys a second just to fill in any definitions you might need, and then we'll keep going. Alright. Again, you can find these slides on my website. Runoff and infiltration. Really not that complicated, so I'll break it down real simple. If water hits the surface and it can seep in or permeate into the soil, it's infiltration. If it can't, it means it's going to have to go somewhere. That's going to be runoff. Couple things for you to think about. If I drop a glass of water and I'm standing in the lawn, well, there's going to be a lot of soil there. It's going to seep in, that's infiltration. If I do that on the driveway, I'm probably going to get a stream of water going down the driveway. That would be runoff. Okay? So, take a second and fill these in, and then we're going to do a little breakdown of runoff and infiltration. Alright, if you have it all filled in, I would go back and probably highlight water over the land. Infiltration, right? This is movement of water into rock or soil. If you pick up on those key details, infiltration in general leads to groundwater. Now, I want you to stop and think about this. We need groundwater in order to get a water supply. So you all can go to leave class and get a sip of water. You all can have water that flows out of the sink at home to wash dishes or any other reason you guys need water. It comes out the ground. It's from groundwater. That requires infiltration. However, as you can see, Long Island is very well populated. Possibly some would say overpopulated. And at one point in time, we had huge tracts of land that were farms. I mean, Levittown Farm, Massapequa Farm. You look at the whole East End. When I was your age, much of it was still farm, and a lot of people made a lot of money making housing developments. Well, every time they do that, every time they convert a farm into a housing community, they go and make roads, and people don't want to mow the lawn, so they put concrete all over the place. And they divert what would have been infiltration to now runoff. That runoff goes into the drains and to lower levels. Suddenly, areas start dealing with flooding issues when big storms come about because the ratio of runoff to infiltration has changed. These are environmental concerns that people need to be paying attention to. So let's look at the next slide. So here we're going to do a little comparison between infiltration and runoff. And I know that the image kind of blocking a little bit of it, but we're going to roll with that. So the intensity and duration of the rainfall. The intensity and duration of the rainfall. If the intensity is great, meaning that it's coming down, you've all been caught out in a downpour at some point, you're going to get a lot more runoff. And you might actually see in the street like the flow of water coming down. I've been out camping with the scouts and we get these torrential downpours and you're trying to run across the field and you're splashing puddles. So even though it's soil, even though there's grass and plenty of area for the water to move into the ground, just the intensity is so great that it doesn't have any choice but to flow over the surface. Flash floods actually work that way. Down in New Mexico 2 summers ago, there were actually a couple scouts, unfortunately, that lost their life because in the middle of the night, crack of thunder, the wall of water came down, and because you have sand out in that desert-type environment, sand has a really slow infiltration rate, or what we'll refer to as permeability, so that that intense rain hit and it all started draining into one area, a lot more runoff, and suddenly you got a flash flood. Another issue is going to be the amount of water already in the soil. So the more time that you have steady rain, the higher and higher the water table is going to rise. And it's kind of self-explanatory. If there's nowhere for the water to go in because it's full, well, then you're going to get runoff. The nature of the surface material. Are we talking about your lawn? Are we talking about concrete? Are we talking about bedrock? Or are we talking about maybe a clay-rich soil? Those two would both lend themselves to runoff. Whereas if you have a really gravelly area, you're going to have a lot more infiltration, right? The loose sediment allows water to pass through quickly. The slope of the land is going to definitely be a factor. If you guys stop and think about your windshield of your car, right, a water droplet hits that and it's going to slide down, sometimes pretty quickly depending on the pitch. Whereas if it's on the hood of the car, it doesn't move as quickly, right? So that would have a gentle slope on the hood of the car, whereas the windshield tends to have a pretty steep slope. And the ground works the same way. The amount and type of vegetation. Vegetation is really good at slowing water flow, and that's why we talked about anchoring vegetation with mass wasting. If you have vegetation, as the water comes through, it's going to be slowed by the plants, by the roots. It's going to allow that water to infiltrate a whole lot better. If there's nothing obstructing the water flow, the water is going to be able to move faster over the surface, and you're going to have a lot more runoff. I'm going to skip the runoff to gully rill formation. I'll talk about that on Monday. All right, types of surface water. Real simple. We got streams, we got rivers. Streams are just going to be any body of water that has a current. That could be a creek, that could be a creek, a bayou, a brook. All these different words that you guys are probably familiar with. Wide classification for all of these fall under stream. When we talk about rivers, though, we're usually talking about a pretty large volume of water, with many tributaries feeding that river or river system. We'll get into that. So, parts of a stream. Originates in the source region, or the other word we like to use is called headwaters. And headwaters, another word for source, is the area at the top of a river that is really going to collect the water and get it flowing downward. We'll learn a little bit more about headwaters when we talk about headwater erosion, which is probably a Tuesday discussion. Good. Source is usually high in the mountains. If you stop and think about it, water up high is trying to come down. Water always seeks the lowest point. So your source is going to start up high, and then through a sequence of tributaries or smaller rivers that feed the main one, they start to come together and draw all that water in, making it larger and larger as it goes. And you may have more than one source. Again, think about mountains. One mountain feeds over to another mountain. They all start to come down in the valley. You got two different source regions into one river. Now this is a pretty basic sketch of what's happening. You see up at the top, you got your river source or your headwaters. Then you have multiple tributaries over in here. All of these tributaries are smaller streams or rivers that are feeding the main line. From there we come down, you got the main river, and you can see that it's winding back and forth and back and forth. That bend in the river, that winding back and forth in the river, is referred to as a meander, or meanders in the plural. To either side of the river is a broad, flat area called the floodplain. Now let's stop and think. Floodplain. What do I think is going to happen on a floodplain? Well, before I answer that, let's ask this question. Do you think it would be a good idea or a bad idea to build a house on a floodplain? You know, a house like this. Or I don't know, the city of New Orleans on a floodplain. Oh, back to what a floodplain is. Oh, that's the area where the water's going to go during a flood when, like, the water overflows the banks of the river, which, by the way, is the definition of a flood, and then pours out in either direction. Well, I'll leave the rest of that for you guys to figure out, but just give that a little bit of thought. The important part about a floodplain is that it's super fertile, because every time the river overflows its banks, it's also going to take lots of ions and nutrients and drop them all over the floodplain. So farming, very good on a floodplain. Farmers like floods periodically. It helps them out. I'm going to skip down to the bottom. We have this area called the mouth of the river, and you can see that it's actually making a triangular shape. We refer to that as a delta. And a delta in math means change. And what actually happens here at the mouth of the river is that there's a change in velocity in the water. When this river comes down and it pours into a larger body of water, it actually slows down and deposits a lot of the material that it's carrying. Therefore, it forms this neat little shape that we refer to as a delta. Also, if this is a saltwater region, right, let's just say that this is ocean down here, this whole area. If this is all ocean, that means that we have salt water. If this is a river, this is going to be fresh water. At some point, you're going to have to mix your salt water and your fresh water, and that actually is in an area we refer to as an estuary. Estuary, it's one of your vocab terms. And in an estuary, you're going to have brackish water. So I just threw a couple words at you guys. You'll see it in your vocab tonight and hopefully lock that in. All right, I'm going to move on. All right, here we got drainage basin and divides. A drainage basin is all the land that supplies water into a particular river system. So in this picture you can see a divide is going to be the higher land on either side that decides, does the water go east or does it go west? The Great Divide in the U.S. is going to be the Colorado Rockies, and that decides whether the water, again, goes east or it goes west. We'll get through a little bit more. I'll recap on that. I got some other examples for you guys, but in general, just be thinking drainage basin, all the land that drains into one area. The other word that we like to use for that is called watershed. Just write that over here. Watershed. Right? That is not where the water boy goes to get more water bottles. Instead, you'll actually see watershed on signs when you're driving along the LIE, because Long Island has a couple different watersheds or drainage basins that supply different areas. So keep an eye out the next time you're in the car. Alright, this next slide is going to talk about stream flow. And we use two words here. We like to use the word laminar when it's in nice straight lines, when it's nice and easy flowing. And turbulent when you get a lot of whirlpools, when it's swashing back and forth, kicking around. So go ahead and fill in what you need to fill in, and then I'll explain a little bit more. So part of why we're looking at this slide is think about erosion. Think about the transport of material. And then how would the flow in a river affect the erosion, right? If it's flowing nice and easy in a laminar flow, chances are you have a pretty straight channel. That tends to be a younger channel. When you have a lot of down cutting, usually water's moving pretty quick, you're going to have that laminar flow, nice straight channel. When you start getting turbulent water, this is when it's going to be moving side to side, and oftentimes you can erode the banks of the river in this side to side motion. That creates those meanders that you saw in the previous diagram. This is an indication that the river is a little bit older. It takes time for the river to develop to that point. Lastly, here we have flow velocity, aka stream velocity. And velocity, usually we talk about the distance compared to time. And here it's just the distance water travels in a given time. So I gave you the velocity formula. You'll need that for physics. V equals d over t. And the same thing works with water. High velocity, by the way, is going to lead to more erosion because the water's flowing faster. It can pick up more grains. It can do a lot more damage. Slower trickling water, not so much. All right, I think we're going to stop there for today. I hope you all have an awesome St. Patrick's Day. And to my colleague, thank you very much for covering my class today. I hope they all behaved. Have a good weekend, guys. Homework's in your backpack.